students, welcome to 60 out of 60 in KCET Chemistry 2025 series. Yes, as you all know, we have started a series where we are going to discuss and explain each and every concept that is going to be asked in your KCET examination, and we are going to solve a lot of PYQs and practice many questions so that you can master all the concepts of chemistry and hit that perfect 60 score in your KCET 2025 chemistry examination. So yes, in today's video we are going to start the second chapter, that is electrochemistry from PU2, and we'll be covering, so this is the part 1, and we'll be covering two important topics, that is galvanic cell and Nernst equation in this video. Okay, so yes, now one request here, one announcement here, please join our WhatsApp channel. The link of the WhatsApp channel will be there in the description section, so please go to the description section and click on the link and then join the channel. It is very important because all the notes that will be provided in our WhatsApp channel, question papers, solutions, everything will be getting in our WhatsApp channel. Okay, so please join that so that you do not miss on any important information. Okay, so yes, I hope everyone is ready now to study and to crack electrochemistry. So please sit with a pen and a notebook so that you can write down every important formulas, every important concepts, and practice some questions as well. Okay, so yes, now let's get started. So the first one here is about this chapter. I'll be telling you how exactly are we going to proceed with this chapter, what are the, how many lectures will be there, in what lecture which topics will be covered, everything. Let us have a understanding of that. Okay, so electrochemistry, again it will be of 3 parts. Okay, the whole chapter I have divided into 3 parts. In the first part, that is today's video, we are going to cover galvanic cell and Nernst equation. Okay, now in part 2 what we'll be doing, we'll be doing electrolytic cell and electrolysis, and we'll be doing conductance of electrolytic solutions. Then coming to part 3, here we have batteries, fuel cells, and then we have corrosion. Okay, so in part 3 we have 3 topics, part 2 2 topics, part 1 2 topics. Okay, so yes, now let us see what is the importance of this chapter, how many questions are asked every year in this particular chapter. Okay, so if you see from 2024 to 2017, right, almost you can say 8 years, 3 questions have been asked consistently from this chapter. Okay, so we can guaranteedly say that we can get 3 questions from this particular chapter. Okay, which is very important. 3 questions means 3 marks you can easily assure if you complete this particular chapter. Now many students fear from this chapter, but I'll tell you, if you know some basic formulas, some basic equations how to write, if you master that, then this chapter is a cup of tea for you. Okay, yes, now coming to part 1 of electrochemistry, that is today's lecture. I told you 2 topics will cover, galvanic cell and Nernst equation. Now let us further break down this and understand what all things are we going to cover. So in galvanic cell we are going to cover construction and working of galvanic cell. So this is not asked in the exam, but I'll make you a brief understanding how this cell works. Next we'll be studying about cell notation. Then we'll be studying measurement of electrode potential, and then we'll be studying calculation of cell EMF. Okay, and then in Nernst equation what all things we'll be doing, Nernst equation for cell and Nernst equation for electrode, and then we'll be studying equilibrium constant. Okay, so one more thing is there here, that is Gibbs free energy. So I'll tell you these topics. Okay, and these topics are very important, and easily you can score marks from these topics. Okay, so now let's get ready. Make sure that you are with a pen and copy, watching, sit silently, stay focused and listen to me and understand this chapter. Very interesting, very exciting, and a highly scoring topic. Okay, now I'm talking about galvanic cell. Okay, so we'll know some properties of galvanic cell. What is this galvanic cell? Okay, one major things that we should know when I'm talking about galvanic cell are, first of all, in galvanic cell, chemical energy is converted to electrical energy. Okay, chemical energy is converted to electrical energy. What does this mean? Some chemical reaction will happen. Now what type of chemical reactions are happening here? Redox reaction. Okay, so redox reaction will take place, and according to that, or with due to these redox reactions, some chemical energy will be released, and this energy will be converted to your electrical energy. Clear? Second one, this is a spontaneous process, means reaction will happen by its own. Okay, reaction will happen by its own. There is nothing need of any external force to cause this reaction. Next, delta G, sorry, this one is delta G is negative. So you know, for every spontaneous process, delta G is always negative, right? So that is why here the Gibbs free energy is negative. Next example of one electrochemical cell is Daniell cell. Okay, so in Daniell cell, we are going to study Daniell cell in detail. I will be telling you what is the structure, what is the working, what is the construction, principle, everything about the Daniell cell. Okay. So now let's move to our first topic in galvanic cell, that is construction and working. So remember, no questions are generally asked from here, but we need to understand how does it work. Okay. So first of all, you need to know that in a galvanic cell, one more, I'll add here one more point, that we need two containers. Okay, you need two containers. Okay, two containers with electrode plus electrolyte. Okay, so a galvanic cell will contain two containers. Okay, in the two containers there will be electrodes and electrolytes. Now let us understand the working, taking the example of Daniell cell. Okay, so now see, this is a Daniell cell. What I'll see, what all things you can observe here. There is a zinc rod, okay, dipped in a electrolyte of zinc, solution containing salt of zinc. So let us assume that it is zinc sulfate. We can take it as zinc sulfate. Okay. Now there is a copper rod on the this side, right hand side, and it is dipped in a solution or an electrolyte of copper, that is copper sulfate. So zinc sulfate is there and copper sulfate is there. Now what happens? I told you this is a spontaneous process, means chemical reaction will happen by its own. So with time what happens? The zinc, okay, zinc rod here comes out as Zn2 plus. Okay, Zn2 plus ions comes out from the zinc rod and leaving electrons here. Okay, on this rod electrons are left. Now these electrons will move like this. Okay, these electrons will move like this and will come here. Right, now what happens in this solution? You can see copper 2 plus ions, right? So these copper 2 plus ions will accept these electrons, okay, and will get deposited on the rod. Okay, so these are copper 2 plus ions that will get deposited on the rod. Clear? So what I am saying, two processes happening. See, Zn is getting converted to Zn2 plus by giving 2 electrons, okay, and copper 2 plus, so copper 2 plus is accepting these 2 electrons and is forming copper. So this is what? Loss of electrons, so we will call it oxidation process, and this is gain of electrons and we will call it reduction process, right? So now what happens? See, what you can observe from the rod, zinc is coming out leaving electrons on the rod. So what will be the charge on the rod? It will be negatively charged. Okay, so this rod is negatively charged, so that is why you can see a negative sign here. Now what happens from this rod? Electrons are going out, copper 2 plus from the solutions are taking the electrons from the rod, so we can say that this rod is positively charged. So that is why we see a positive charge here. Okay, now this electrode where oxidation takes place, okay, remember this definition is always valid. Anode is what? Anode is that electrode where oxidation takes place, and cathode is that electrode where reduction takes place. Okay, so now if you can tell me which is anode and which is cathode here, tell me. Oxidation is taking place in zinc, so which is my anode in this particular case? Zinc is the anode, and where reduction is taking place? At copper, so the cathode is copper, right? Now zinc, what is the charge of the zinc? We have discussed here negative charge. So zinc is your negatively charged and cathode is your positively charged. Copper will be positively charged electrons. Next, from which side the electrons are moving? The movement of electrons is from, see, electrons are produced from here and moving like this, right? So movement of electrons will be from zinc to copper, right? And you might be knowing that the direction of current is opposite to the direction of flow of electrons. So if electrons are moving in this direction, current will be in opposite direction. So what is the direction of current? So current direction is from copper to zinc, right? Very simple working, student. There is a zinc rod dipped in a zinc solution. There is a copper rod dipped in a copper solution. Now zinc will lose electrons and Zn2 plus will come to the solution. Then the electrons present in the rod will move through the external circuit and come to the other side. Copper 2 plus present in the solution will run and take these electrons, okay, and get reduced and now stick to the copper rod. So with time what will happen? Zinc rod will become thin, copper rod will become fat, right? So that is what is happening. Now coming about the sign convention. Because here electrons are produced, this is negatively charged, this is positively charged, and here oxidation is taking place, so that is anode, here reduction is taking place, so that is cathode, okay. Now here I will tell you a very nice trick to remember these things, okay. So I will write one abbreviation, that is lone. Remember, L stands for left, okay, left side. O stands for oxidation. So left side oxidation is taking place. Where oxidation is taking place, that electrode is called as anode, okay. Now what is the charge of this electrode? It is negative, okay. I hope you have remembered. Those who have remembered, I want everyone to comment lone and write the abbreviation again so that you will never forget it again, okay. Let's see how many of you have remembered this. Please comment down lone and its abbreviation, okay. Fine. Now coming to next one here, okay. Now ma'am, every time do we have to do this much big diagram to represent a cell? My answer is no. Here we can represent the cell by a method called as cell notation. There is a proper, okay, one more thing I forgot to tell you. In this diagram, what is this U-shaped tube? This U-shaped tube is called as salt bridge and it is used to complete the circuit, okay. This circuit is now complete. That is because of this salt bridge, okay. So now let's come back to our topic, that ma'am, do we need to draw this diagram every time to represent a cell? Answer here is no. There is a proper method how we can represent this cell, okay, and that is called as cell notation, okay. So now what is cell notation? So I can write cell notation is nothing but representation of cell, okay. Cell notation is what? Representation of cell. Now how does it take place? Very simple, we just have to follow a order, okay. Let's see, we'll start from this rod. What is this rod made up of? Zinc. So I'll write zinc. What is its physical state? It is solid, so I'll write solid. Now zinc rod is connected it with ZnSO4, okay. ZnSO4, what is the ion here? So we have Zn2 plus ion here and we have copper 2 plus ion here, right? So zinc rod is connected to Zn2 plus, so after zinc rod I'll write Zn2 plus. This is present in the solution phase, so I'll write aqueous solution. Now Zn rod over, this solution over. Now comes what? The salt bridge here. So salt bridge is represented by a double line. Now this Zn and Zn2 plus are separated by a single line, okay. This is represented by single line, the salt bridge is represented by double line. Now this salt bridge is connected with what? Copper 2 plus, so we'll write copper 2 plus, its phase is aqueous, so aqueous. Next it is coming to copper, right? So this is aqueous phase, this is solid phase. So again one single line will come, then copper, then the physical state of copper. Once again let's try, okay. Zn rod, Zn solid, Zn in connected with Zn2 plus, Zn2 plus connected with U-shaped tube, so double bar to copper 2 plus, copper 2 plus to copper, right? You have to represent the phase, different phase with a single line, salt bridge with a double line, and you need to mention the physical state of this one, whether it is aqueous, whether it is solid or not, okay. Fine. So that is cell notation. Now this whole diagram can be just represented with this one single line. So what does it tell here? See what all information we can get. It is saying that this side, left side, this is the left part and this is the right part, right? So we have written LOAN, right? So left side, what is happening? Oxidation. Who is undergoing oxidation here? Zinc. And this side, reduction. Who is undergoing reduction? Copper, right? Next, so which is the anode here? Anode is your zinc and cathode is your again copper, right? Here what is the charge of zinc? Zinc is negatively charged and copper is positively charged. So just by seeing the cell convention we can derive all these data, right? Okay. Coming to next topic, measurement of electrode potential. Now first let us understand, ma'am, what is this electrode potential and why do we need to measure it? Okay, so yes, see, first let us understand what is electrode potential. What happens here? If you see, I told you that zinc will come out, right? Zinc will come out. What I will get here? Zn2 plus, right? And here that is negatively charged, right? So now you see there is a charge difference between this rod and the solution. The rod is negatively charged and the solution is positively charged. So this charge difference, due to this charge difference, there is a potential difference created and this difference is called as electrode potential. Clear? What is potential difference? What is electrode potential? I'll write in simple words. Electrode potential is the potential difference between the rod and electrolyte. You can write rod or you can understand electron. Between the electrode and the electrolyte, the charge difference, the potential difference is called as electrode potential. Now if you see on this side how it is there, so this side what happens? You have this side copper 2 plus, right? So these copper 2 plus are going and depositing and here we have electrons, right? So that's the charge difference here also. So because of this charge difference, so what happens? Because of this charge difference, a potential difference is generated and that is called as your electrode potential, right? Now what happens here? Okay, now here I'll correct. Now what happens here? This charge, this rod is positively charged, right? And here we have negative ion SO4 2 minus, right? So now there is a charge difference. The rod is positively charged, the ions are negatively charged. So again here is a difference of the charges due to which a potential difference is there, and this one is again called as your electrode potential. So we have an electrode potential here, we have an electrode potential here. Now this side, because oxidation is taking place, okay, this potential is called as oxidation potential, okay, and because your reduction is taking place, this potential is called as reduction potential, okay. Now let us see about electrode potential in detail. A potential difference develops between the electrode and the electrolyte, which is called as electrode potential, okay, that we have already discussed. Now when the concentration of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. Now what it is saying? This concentration of the electrolyte, okay, the concentration of the electrolyte, if it is 1 unity, 1 molar, if it is 1 molar, here if it is 1 molar, then the same electrode potential what we were calculating before, now we will give it a special fancy name as standard electrode potential. So what is the condition of standard electrode potential? The concentration of the electrolyte should be 1 molar, okay. Next, standard electrode potentials are now called as reduction potentials are now called as standard electrode potential. Now what is this one? See, as I told you, there is one oxidation potential, there is one reduction potential. So to avoid these type of confusions, oxidation potential, reduction potential, IUPAC has solved this problem by telling that whether it is undergoing oxidation or it is undergoing reduction, we will represent always the electrode potential in the form of reduction potential. Suppose it is asked to show the reduction potential of zinc, okay, then it has to be shown, to show the electrode potential of zinc, then it should be shown in the form of reduction potential. Now I will show you how this happens, okay. Okay, so now let us see how to represent the reduction potential, okay. See, for zinc the electrode potential is represent like this, okay. Now what is this? E stands for electrode potential. E naught stands for, this naught stands for standard electrode potential. Now Zn to Zn2 plus if I write, what is this undergoing? Zn to Zn2 plus, it is undergoing oxidation. So actually this is representing oxidation potential. But IUPAC told no, will not do like this. Every electrode potential should be represented in the form of reduction potential. So that is why what we have to do is, the correct way of representing is now not like this, rather like this. Okay, reduction potential. For copper there is no problem, that is undergoing, so copper 2 plus 2 copper. Okay, so this is how we represent the reduction potential. Now how to measure this value? How do we measure the value of this potential difference, and this potential difference how do we measure? So for that we need a reference electrode, and we use a hydrogen electrode for this. So now see, according to convention, a half cell called standard hydrogen electrode represented by this one. So this is how the standard hydrogen electrode is represented, is assigned a zero potential at all temperature. Okay, now one more thing I'll tell you why we are studying this, everything will be clear, little confusing, but don't worry, stay with me for next 5 minutes, everything will be clear. Okay, so now another story has come here, that IUPAC has done that, not IUPAC, according to convention it was taken that a hydrogen electrode we will prepare. Okay, and we will assume that this hydrogen electrode potential, okay, like the potential will be there here. Suppose we have hydrogen electrode, one second, yeah, suppose here I have hydrogen electrode and here I have H plus, right? So there is a potential difference here also, but this one I will consider as 0 by convention. We will do it like this. Okay, clear? Now we will see how to measure the electrode potential. Till now what we have understood, what is electrode potential? Between the rod and the electrolyte, whatever potential difference is generated, that is called electrode potential. There are two types of electrode potential, oxidation and reduction. But IUPAC said no need to do so much convention, so much confusion. We will always maintain one form, that is reduction potential. So whenever you are telling the potential of any electrode, we have to mention it in terms of reduction potential. Okay. Next, coming to another story has come, that one thing is there, one hydrogen electrode is there and its potential is assumed to be 0. Okay, this much story has been covered till now in electrode potential. Now let's move further. Now see, this is how we are measuring the electrode potential. Okay, so what we have taken, on one side you have to take the hydrogen electrode and the other side you have to take the rod whose potential you want to measure. Okay, for example, I want to measure zinc electrode potential, so I dipped zinc rod, salt of zinc, then hydrogen electrode and the hydrogen solution. Okay, now here it is a voltmeter, so this will measure the potential difference between these two, right? Now let us see. It is measured with the help of a reference electrode known as the standard hydrogen electrode, abbreviated as SHE. The standard electrode potential of an electrode can be measured by pairing it with the SHE and measuring the cell potential of the resulting galvanic cell. So now what happens, I will come back to this, but just remember now that we are taking two containers, one side we will take hydrogen electrode, other side you have to take that electrode whose potential you want to measure. Then the voltmeter will tell you the difference between these two potential, and what answer comes here, that will be the electrode potential of the zinc. Because this is assumed to be 0, so whatever values come here, that will be the electrode potential of the zinc here. Getting this point? Once again let me repeat, it may not be clear to everyone, let us understand it again. I am talking about electrode potential. What is electrode potential? Whenever there is an electrode, there is an electrolyte, there is a charge difference between these two. This difference of charge creates a potential difference called as electrode potential. There can be oxidation potential, there can be reduction potential. To avoid confusion, your IUPAC has said that we will always represent the electrode potential in terms of reduction potential. When I am saying in terms of reduction potential, it should be written like this: E naught Zn2 plus 2 Zn. We have to show reduction here. E naught of copper 2 plus 2 copper. E naught of Ag plus 2 Ag. E naught of Ni2 plus to Ni. Getting? So this is how the electrode potentials are represented in the form of reduction potential. Now how to calculate these values? Nothing. I want silver electrode potential, connect silver on one side, collect hydrogen on one side, calculate the voltmeter will tell you a value, whatever it is giving you, that will be the reduction potential. Clear? So that is how we can calculate the reduction potential of different electrodes. Okay. Now coming to the next one, that is calculation of cell EMF. Now what is this cell EMF? You have seen many batteries, they will be written 5 volt, 2 volt, 3 volt, 10 volt, right? So what is this cell EMF? So I told you there are two potentials, oxidation potential and reduction potential. So cell EMF is nothing, the potential difference between the two electrodes of a galvanic cell is called as the cell potential and is measured in volts. Okay. The potential difference between the two electrodes of a galvanic cell. We have two electrodes, so the potential difference, this side one potential difference is there, this side one potential difference is there. If you take the difference between these two, then whatever we get, that is called as cell potential and the units of this is called as volt. Okay. Next, the cell potential is the difference between the electrode potentials, that is the reduction potential of the cathode and anode. Okay, so what's the formula for this? So E of the cell is E of the cathode minus E of the anode. Okay. Now if you remember, cathode was on the right hand side, anode was on the left hand side. So I can write E of the right side minus E of the left side. Okay. Getting? So this is how we can calculate the cell EMF. Till now what all things we have discussed? Galvanic cell, what is electrode potential, the two electrode potentials, how to get using SHE, that is standard hydrogen electrode. Then after getting the two electrode potentials, if we subtract them, we will get the cell EMF. You need to subtract cathode minus anode or right minus left. Getting? Okay. Now let's have a quick revision of what all we have studied. I am doing this because you can recollect the concepts once again. Okay. So the first one here is in galvanic cell, the chemical energy is converted to electrical energy, first thing. Second point, it is a spontaneous process and delta G is negative. Next one, at anode oxidation will take place, at cathode reduction will take place. Always remember this one. Okay. Next, for this particular cell, anode is having negatively charged and cathode is positive charge. For which one? For galvanic cells. Okay. Not every time. So if somebody asks you what is an anode, you need to answer anode is that electrode where oxidation takes place. And in galvanic cell, anode is negatively charged. But anode is not every time negatively charged or not every time positively charged. Okay. Next, cell notation, the way of representing the cell, how to represent it, will start from the left and will end at the right. Next, electrode potential, what is electrode potential? Between every electrode and electrolyte there is a potential difference. That difference is called as electrode potential, and the IUPAC has told that we should represent the electrode potential in terms of reduction potential only, and to measure the electrode potential we need a standard hydrogen electrode. Okay. Next, cell EMF, how to calculate? We have by using standard hydrogen electrode we will get both the EMF, right? Then what we can do, we can just simply subtract them, right minus left or cathode minus anode, and if we subtract them we will calculate the cell EMF. Clear? Okay. So now let us try a small question. Let us see whatever we have done whether we have understood or not. So there is a reaction given to you. You need to write the half cell reaction. Half cell reactions means you need to write the oxidation half and the reduction half formula, right? Now oxidation, if you see from copper to copper 2 plus, what is happening? The oxidation number is increasing. Here it is 0, here it is 2 plus, so this is oxidation. And if you see Ag plus to Ag, here it is plus 1, here it is 0. Plus 1 to 0, the oxidation number is decreasing, so this is reduction, right? So now let us write the half cell reaction. So oxidation reaction, if I write oxidation reaction, that is copper is undergoing copper 2 plus, right, with the loss of 2 electron. So you should remember oxidation is loss of electron. Okay. Then reduction, for reduction what is there? Gain of electrons. Okay, now who is gaining electron? Silver. Ag plus to Ag, reduction is for silver. So what I'll write? Ag plus 1 electron is equal to Ag. Now here we need to remember one thing, that the number of electrons lost should be equal to number of electrons gained. So here 2 electrons are lost, means here also 2 electrons should be gained. So what we can do, we can multiply the whole equation with 2. Getting? So this is my half cell reaction, oxidation half cell reaction and reduction half cell reaction. Now if you know where oxidation half cell reaction will take place, this will take place at anode, right? And this will take place at cathode. Okay, so this one will do. So this is done. Now cell notation. So cell notation, you just need to start from you need to write the oxidation part on the left hand side, then give a double line, and reduction part on the right hand side. So we know what is the oxidation part, copper 2 plus. So I'll write copper, right? Copper is in solid state, copper 2 plus, aqueous state, then I'll do a salt bridge, right? Then Ag plus to Ag, reduction part. So Ag plus, that is your aqueous, and then Ag, this is your solid, right? Copper 2 plus, double line, then Ag plus to Ag. This is your oxidation part, that is your reduction part. I think everyone is getting this. Okay, next, expression to calculate the EMF of the cell. So yes, EMF of the cell, how to calculate? I'll write E of the cell is equal to E naught of cathode minus anode, and I should write it in terms of reduction potential. So which is the cathode? Right hand side is cathode, silver one. So I will write E naught, or reduction potential of silver, right? Cathode, this is your cathode, minus E naught of anode, that is copper 2 plus to copper, right? So this is your anode. So here I will erase little bit and make it, we'll mention oxidation here this side, and this is oxidation state. Okay, so we have got all the 3 half cell reactions, you know how to write, but just by seeing the equation you can say this is undergoing oxidation, so this is oxidation reaction, this is reduction reaction. Cell notation, oxidation side, then that side reduction side, then expression to calculate EMF, E naught of silver minus E naught of copper. Getting? Okay, now let's move forward. Question is there for you. An electrochemical cell generally consists of a cathode and an anode. Consider the correct statement with respect to cathode. Okay, so oxidation occurs at cathode, is it correct? No, I told you lone, right? Oxidation takes place at anode, so this statement is wrong. Next, electrons move into the cathode. If you have seen here in galvanic cell, electrons were moving out from the anode and were accepted by the cathode, right? So electrons move into the cathode, this is a correct statement. Next, usually denoted by a negative sign. So does cathode is usually denoted by negative sign? There is no rule like that. Just now we saw in electrochemical cell, in galvanic cell, cathode always is positively charged, right? So this statement is also wrong. Next, is usually made up of a insulating material. It is also not correct. Just now we saw copper was the cathode, which is not an insulating material, so that has no relation here. Okay, so now let's go to the next one. We'll come to Nernst equation. Now before understanding anything about Nernst equation, a very simple calculation, simple thing I'll tell you what is all about Nernst equation. Nernst equation is also used to calculate cell EMF. Now your question may arise, ma'am, just now we learnt a formula to calculate the cell EMF, that is E naught of cathode minus E naught of anode. Then why again this one? So yes, this formula is used when the conditions are non-standard. Now ma'am, what is this non-standard conditions? Non-standard conditions means the electrolyte concentration. You remember we were having like this 2 containers we were having, and we were having a electrode, and then we were connecting it, we had a salt bridge, right? And here I was having electrolyte. So if these electrolytes are 1 molar, then we call it standard conditions. But if they are not 1 molar, they are having different concentration, then we call it non-standard conditions. So if the cell is in non-standard conditions and we want to calculate the cell EMF, we cannot use that formula. We need to use the Nernst equation here, right? So Nernst equation is to calculate the cell EMF under non-standard conditions. Okay. So now let us see Nernst equation is what? Nernst equation is again for two types. One is for electrode and the other one is for cell. So Nernst equation can be written for a single electrode, that is one side, okay, and can also be written for the complete cell. Okay. So we'll see both of that in the next slide. Now see, for single electrode I want to show you. So this is what metal undergoing reduction, Mn plus, gaining of n electrons to get M solid, right? So Nernst equation for this, how will it look like? See, so this is your electrode potential of this particular electrode. This is the electrode potential under the standard conditions, minus RT by NF log of concentration of M divided by concentration of Mn plus, product concentration divided by reactant concentration. Now here you have to remember that for pure solid, the concentration of pure solid is taken as 1, right? So if I now modify this equation, I will get E naught, E of Mn plus minus M by Mn is equal to E naught minus RT by Nn log of 1 by Mn plus, right? Okay. Now I'll simplify this equation for you. Okay. So now see, this is what? This is the electrode potential under non-standard conditions, right? This is the electrode potential under standard conditions, right? So you remember, non-standard condition electrode potential will always be standard electrode potential minus something, right? So that is why I can say the standard electrode potential is a greater number, or the standard electrode potential is more than the non-standard electrode potential. Now here what happens, R value is 2.303, okay, R value is 2.303, T is 25 degrees Celsius, 298 Kelvin, and we need to calculate, and F is 96500. So now if I substitute all these values, what I'll get is E of the electrode, so I'll write Mn plus to M is equal to E naught of Mn plus to M, okay, minus 0.059 by N, okay. I have converted this to log also, so log 1 by root over 1 by Mn plus concentration. So wait, I'll write it other side so that it is clearly visible, because this is what we are going to do in the question. So this is the formula that we are going to use. So E of the rod, non-standard, okay, is equal to E naught of Mn plus to M minus 0.059 by N log of 1 by Mn plus concentration, okay. So this, remember this formula, this is what we are going to use in our question, okay. This formula we are going to use in our question, okay. For single electrode, this is how we can calculate. Now coming to a cell, if a cell is there, okay, this is a representation of a cell. For cell, how to write the electrode, potential, or the E of the cell. So E of the cell is equal to E naught of the cell. How will you calculate the E naught of the cell? E naught of cathode minus E naught of anode, minus 0.059 by N log of product concentration. So we will only consider the ions here. Product concentration Na2 plus divided by the reactant concentration Ag plus, and here you should remember, this is where all the students forget, okay. This is important here, that this stoichiometric coefficient should be taken as the power, okay. So stoichiometric coefficient should be taken as power, and we will get this type of equation for a Nernst equation, that is a cell under non-standard conditions. Clear? Once again let me repeat, Nernst equation is the equation to calculate the cell EMF when the cell is not under standard conditions. What I mean by that, when the electrolyte's concentration is not 1 molar, in that case we have to use Nernst equation, okay. So now coming, N is what here? N is the number of electrons used, okay. Now next we have to take only ions, product ions divided by the reactant ions. If there is any stoichiometric coefficient, that also need to be considered, okay. Fine. Now let us go to the question here. One question is there. The electrode potential of copper electrode dipped in 0.025 molar of copper sulfate solution at 298 Kelvin is. Standard electrode potential of copper is 0.34 volt. Now by seeing this question, what do you think? Is it a rod electrode potential or it is the electrode potential of a cell? You see, it is only talking about copper, right? So it is a single electrode potential. So we know this formula, Cu2 plus 2 electrons will give you copper. Okay, now the concentration of copper given to you is 0.025. Okay, now let us calculate. We have E is equal to E naught minus 0.059 by N is 2 log of 1 by copper 2 plus concentration, that is copper 2 plus concentration. So I will write here N, okay, so that we can know what we are substituting. Okay, now if I use this one, so what is E value? I have to calculate. E naught value is 0.34, okay, minus 0.059 by 2 log of 1 by copper 2 plus concentration is 0.25 molar. So I can write it as 2.5 into 10 to the power of minus 2. Okay, so now you can solve this. Okay, so now if you solve this, you will be getting around okay, one more thing we can see that so now if you solve this, you will be getting around 0.293. okay, so the correct answer for this question will be option number B. Okay, so yes, this is how you can see this is Nernst equation for a single electrode. Now let us move forward here. Another question is there from Nernst equation of a cell. Okay, Nernst equation for a complete cell. So copper 2 plus concentration is given, Ag plus cell. So the cell here, the anode part is copper, the cathode part is Ag. E naught of copper is given, E naught of silver is given, and we need to calculate E of the cell. Okay, so again let us use the complete equation. We have E of the cell, okay, is equal to E naught of the cell, right, minus 0.059 by N. N is this log of products by reactants. For that we need to write the equation correctly. Okay, so if I write the equation, oxidation is what? Cu is getting converted to Cu2 plus 2 electron. Then we have Ag plus getting converted, Ag plus 1 electron is giving you Ag, right? So you can multiply 2 here because I told you that the number of electrons should always be equal. Now this is happening on the left hand side, so this is oxidation and this is your reduction, right? So this is reduction. Now we can add these both. Now if you add this both, you can cancel 2 electron, so this is copper plus 2 Ag plus, okay, that is giving you copper 2 plus 2 Ag. Okay, now let us write the equation. Which ion has come on the product side? Copper 2 plus. So I will write copper 2 plus concentration, and then reactant side Ag plus concentration, and you see there is a power 2. So here I have to mention 2. Okay, so now I can substitute the values. Copper concentration is 10 to the power of minus 3. Okay, and Ag plus concentration is 10 to the power of minus 5. Minus 5 into 2, so that is 10 to the power of minus 10. Now this will go up, right? So we'll get 10 to the power of 7. So from this we can easily eliminate these two options, right? Now if you see 0.46 minus term is there, so this one will be there, this one will not be there. So the correct answer for this question will be option number 2. Now I told you if we substitute this R, T and F, we'll get 0.059 and we can convert log to ln. Okay, so that is why the correct answer for this question will be option number 2. Okay, now let us go to the next part, equilibrium constant. Okay, so when the cell is at equilibrium, what do you mean by cell is at equilibrium? That the two when the cell is at equilibrium, the E of the cell becomes 0. Okay, the E of the cell becomes 0, the cell do not function further. Okay, now what happens at this time? E of the cell will become 0. Now you can see from the Nernst equation, we had this one, E of the cell equal to E naught of the cell minus 0.059 by N log of. Now when the cell is at equilibrium, the concentration of ions can be represented as log of K, equilibrium constant. Okay, so now this part is 0, so I can write this is equal to 0. So what will happen? E naught of the cell is equal to 0.059 by n log k. Now what is k here? You should remember k is equilibrium constant. Okay, k is equilibrium constant. So this is a very important formula. Many a times questions have been asked from here. Okay, now let us see the next formula for today. Gives free energy and E naught of the cell. What is the relation? So gives free energy, delta G is equal to, so this is not typed properly, I'll write here, delta G is equal to minus NF E naught of the cell. Okay, and delta G is also equal to minus 2.303 RT log of K. Okay, so these two formulas are very important and many questions have been asked from here. So please remember these two formulas definitely. Okay, more than Nernst equation questions have been asked from here. Okay, now let us do some question here. So H2, one cell is given, E naught of the cell is given to you. You need to calculate the equilibrium constant. So what's the relation? We know E naught of the cell is equal to 0.059 by n log of k, right? This is the formula. Now you see how many electrons have to be used here. If you see, H2 is getting converted to H plus, right? Here it is 0 and here it is plus 1. So how can I write the oxidation part? Oxidation reaction, H2 is getting converted to 2H plus by the loss of 2 electrons. And if you see Ag is there, Ag plus is getting converted to Ag. So that is reduction here, right? So what I'll get? Ag plus 1 electron is giving you Ag. Now here number of electrons should be same. So this is 2, right? So now what is the n factor? N factor is 2. So I can write here 0.059 by 2. E naught of the cell is how much? 0.22 volt. Okay, that is equal to log of k. So now if you solve this, we can calculate this, and I can, so for easy calculation, let me consider this as 0.06. Okay, just for easy calculation. So how much I'll get? 0.03, and this is 0.22. So I can say something about 7 point something I'll get log k. Right, log k will be 7 point something, then k will be equal to what? 10 to the power of 7 point something. That antilog, if we take 10 to the power of 7, so you can see this is the here 10 to the power of 7. So the correct answer for this question is option number A. You need not solve completely, you can easily understand. Suppose 7 point x I will write, 7 point x, here it is 7 point x. Now if you take antilog, how we will write? 10 to the power of 7 into 10 to the power of x. Right? So 10 to the power of x will have some value, that can be anything, but power will remain 10 to the power of 7. There is only one option with 10 to the power of 7. So the correct answer for this question will be option number A. Okay. Now coming to, okay, so now we have covered today's topic. So let us do some practice questions. Before that, this was a homework question that I gave in my last video where we were doing solutions chapter. So this question is about osmotic pressure, right? So if you remember, osmotic pressure formula is pi is equal to CRT. Now C is the molarity. But here if you see what is given, 3 gram of glucose means W2, that is 3 gram. And then we have molar mass, that is M2, 180 gram. Okay. And then we have 60 gram of water. So 60 gram of water is W1. But for molarity, actually we need volume of the solution, but there is no information regarding the volume of the solution. So in such cases, we can consider molarity, okay, almost equal to molality, and we need to solve the question accordingly. Okay, so now let us put the molality formula here. So mass of the solute by molar mass of the solute into 1000, okay, by mass of the solvent, that is 60, then into R 0.0821, or I can say 0.083. So we have 0.083, and then temperature is for 15 degrees Celsius, right? So you need to convert 15 degree to Kelvin, 273. So we'll get 288 Kelvin here, right? So now if you multiply and solve this, we'll be getting around 6.5718. So the correct answer for this question will be option number A. Okay. Simple question, but little calculation involved. Okay, now let us practice the PYQs from electrochemistry questions. So which of the following is incorrect in a galvanic cell? Okay, oxidation occurs at anode, that is correct. Lone, do you remember lone? Oxidation at anode. Reduction occurs at cathode, this is also correct. Electrons at which, the electrode at which electrons are gained is called cathode. Yes, if you remember, we have this side, and we have like this here, right? This side this is anode and this is cathode. Here electrons are lost and here electrons are gained. So the electrode on which the electrons are gained is called cathode, that is correct. The electrode at which electrons are lost is called cathode, this is wrong, this has to be anode, right? So the correct answer for this question will be option number D, because you need to find the incorrect statement. Okay, now let us move towards the next question. Consider the following 4 electrodes, the reduction potential in volts of the electrode in the order. Okay, here different electrodes are given. We know for electrodes it is E of the electrode is equal to E naught of the electrode minus 0.059 by N log of 1 by Ag plus concentration, right? So now let me put the values here. For E naught value is 0.8, so we'll do it option to option wise. Okay, so first option, if you see, this one will be 0.08, okay, 0.8 minus 0.059 by 2 log of 1 by, what I have to substitute for option A, 10 to the power of minus 3, right? So this will go up, it will become 3, so I'll say 0.8 minus 0.059 by 2, okay, then 3, right? So I can write it as 0.8 minus 3x. This term I have taken as x. I'll tell you why. Now coming to option number B. If you proceed in that way, we can write it as 0.8 minus 1x. Okay. Coming to option C, 0.8 minus 2x. Because here 10 to the power of minus 2 will come, 2 will go up, then 2 log 10, that is 2. Then here you will see 0.8 minus, we will have here some error, 1 second. Okay, so this one was a 0.0001, okay. So yes, this will become 4x, one small error in the question, please correct it. This is 4, so I'll get here 4. Right, so this one will also become 4. Yeah, so now this one will become 3x. Now you see, from this we are subtracting a number from 0.8. So where we are subtracting the smallest number, there the potential will be highest, right? So that is why we are subtracting a smaller number here, right? So this has to be the highest potential, because from 0.8 we are subtracting a very small number here. So the potential will be higher in B. So in all the options you see, these are all wrong, because B is the correct answer. B will have the highest. Then we are subtracting this one, so next will C, then 3, that is D, and then 4x, that is your A. So the correct answer for this question will be option number A. So for this question I will mark it as hard, because little you need to know this calculations, how to do it very easily. Otherwise you will put the values, you will calculate, then it will take a long period of time. Okay. Now coming to question number 3. For Cr2O7 2 minus 14H plus 6 electrons, chromium 7 water, E naught value is given, chromium concentration is given, and chromium 3 plus 15 millimole concentration is given, E of the cell is given, pH of the solution is nearly equal to. Okay, so again let us have to use the Nernst equation. E of the cell is equal to E naught of the cell minus 0.059 by N log of, what are the ions you can see on the product side? Chromium is there, right? So I can write Cr3 plus square, don't forget to put the power, don't forget here. And on the reactant side, if you see, Cr2O7 is there and H plus is there, right? So Cr2O7 2 minus is there, and then we have H plus, right? The power is 40. Clear? Now if we solve this, and number of electrons you can see it is 6 electrons, so I will put here as 6, okay, and E value is how much? 1.067, and E naught value is 1.33, okay, minus 0.0, let us for easy calculation I'll take a 0.6, okay, into 6 log of What is Cr3 plus concentration? Cr3 plus concentration is 15 millimoles, right? 15 square is there. Then Cr2O7 is 4.5. Okay, and then here we have H plus concentration to the power of 40. Okay, so from this you need to calculate the H plus concentration. After that, like if I do the calculation completely, you can see here. Okay, so now if you see, what I can do is I'll take this completely to this side. So I'll get 0.01, okay, log 15 into 15, then we have 45 into 10 into H plus to the power of 14 is equal to 1.33 minus 1.067, right? So this will be around 0.263. Okay, now I'll divide this one to this side. So I'll get 0.263 divided by 0.01, right? So that is 263. Here we can write it as 1000, 1 by 100. So it will be around 26.3. So I am writing it, erasing it, so that space will be there. So this one will be 26.3. Okay, now this side what is there? 15 ones are, 15 threes are, 3 ones are, 3 fives are, right? So yeah, so we have log of 50 minus log of H plus to the power of 14, right? So now what is log 50 value? Log 50 value is 1.69 minus 14 log H plus, right, is equal to 26.3. Now if I calculate this one, what I'll do, I'll take this 1.69 to this side. Okay, so almost 1.7, 26.3 plus 1.7 is almost 28, right? So now 28, and we have here log of minus log of H plus, and this 14 I'll divide here. So I'll get 2. Now minus log of H plus is pH. So pH is equal to 2. So the correct answer for this question is option number A. Now how I got log 50 is 1.69. So that you not worry, these values will be given, or you can also calculate like this, log of 5 into 10, right? Log 5 is 0.69, log 10 is 1. So log A plus log B, 1.69 will get. Okay. Now coming to next question. So this question also I'll mark it as little hard because it has lot of calculations. Next, coming to question number 4. So Fe32 plus to Fe I is given, this one is given, equilibrium constant for the reaction taking place in a galvanic cell consisting of the above 2 electrodes. Equilibrium constant. So we know what E naught of the cell is equal to 0.059 by n log of K. Right? Now what is E naught of the cell? Now how, yes, here the trick is lying. How to identify which is cathode and which is anode, because here no cell notation is there, no cell reaction is there, right? So in this case what we can do, you have to check the electrode potentials, okay, electrode potential of both the electrodes. Which is having higher electrode potential, that will have the more tendency to get reduced, and that will behave as a cathode. So what I am saying, higher the reduction potential, higher reduction potential will be the cathode. This you should remember. Okay, so this is one learning that you need to take. Higher reduction potential will be cathode. So this is your cathode, this is your anode. So E naught of the cell will be what? Cathode minus anode. So I will get 6 minus 5, 1, and I have 7 minus 5 is 2, 0.021. Next, 0.0, so they have told this value you have to take at 0.06. So for easy calculation, we can consider this as 0.06. Okay. Next, n factor is how much? So you can see that n factor is 2 because one second. Okay. So now if I write the reactions quickly, if I write the reaction, Fe3 plus is getting converted to Fe2 plus, right, with the gain of 1 electron. But if you see, I2 is getting converted to I minus, right? So it will be like this, I minus will get converted to I minus, one second, okay, I'll write on this side. So we have to write the oxidation. So I minus to I2 is oxidation, I2 to I minus is reduction. These all are reduction potential, right? So I can write 2I minus will lose 2 electrons to give you I2. So this equation should also be multiplied with 2 because number of electrons should remain same. So n factor is 2 here, right? So if I say this will become 0.03 log k, right? So if I divide, it will become 7 is equal to log k. So then k will be equal to 10 to the power of 7. So the correct answer for this question will be option number D. This question also has little calculation, but again not very difficult. You just need to know which one should be cathode and which one should be anode. Okay. Now coming to the next question, for a cell involving 2 electron changes, so n is equal to 2. E naught of the cell is 0.3 volt at 25 degrees Celsius. The equilibrium constant of the reaction. So again we have the same formula here. E naught of the cell is equal to 0.059 by n log of k, right? So now E naught of the cell is how much? 0.3, okay, 0.059. Here also for easy calculation, let us take as 0.06, okay. So we'll take it as 0.06, n is 2, right, because they have told you already 2, and then log of k. Now if you see, this is 0.03 and here it is 3 by 10 I can write, and this is 3 by 100, so it will be 100 by 3, so I'll get 10, right? 10 is equal to log k. Then what is the value of k here? K will be equal to 10 to the power of 10. So the correct answer for this question will be option number D. Okay. So yes, these are the important questions. So now let's do a small revision of what we have studied very fast. Okay. So first we have studied about galvanic cell. In galvanic cell we studied the construction and working. Then we studied the cell notation, how to represent a cell. You know, you have to start from the left hand side and come towards the right hand side. Then measure in the cell notation, left side is about anode, right side is about cathode. Then we studied about electrode potential. We know that to measure a electrode potential we need a standard hydrogen electrode, and we also discussed what is electrode potential. So electrode potential is the difference between the electrode and the electrolyte, the potential difference between these two. Next we also did calculation of cell EMF. What's the formula for this one? E of cathode minus E of anode is equal to E of the cell, right? Now coming to Nernst equation, we studied Nernst equation for a rod and the Nernst equation for a complete cell, and then we have equilibrium constant, how to calculate at equilibrium. The E of the cell becomes 0, so E naught of the cell, we now got the equation, and we have also got the equation for Gibbs free energy. Okay, so now I'll give you the very important thing, the formulas that you need to remember. Okay, so I'll tell you, this is the formula for E of the cell, E naught of cathode minus E naught of anode, then Nernst equation, okay, Nernst equation, and then you have E naught of the when the cell is at equilibrium and the relation with the delta G. Okay, so please note down all these formulas, very important. And yes, if you have any doubt, okay, one more thing, this is a homework question for you. Please try this question and comment down the answers definitely. Let's see how many of you are doing it correct. Okay, so yes, if you are enjoying the classes, if you have understood everything, then please like, share and subscribe the channel. And also all the very best for your KCET 2025 examination. And one more thing, please student, work every day so that you can hit that perfect 60 score in your KCET chemistry examination. Okay, if you have doubt in any of the concepts that we have discussed today, if you have not understood any question, please comment down, I'll definitely address it. Thank you for watching, and once again please subscribe the channel for more updates.